Okay, so what I'm going to start doing on the examples this week, I think, is I'm going to try and tie each example to a problem that you're doing on your assignment. So, for example, this first example that we're going to do is similar to assignment number 14. So, remember your assignment today was numbers 11 through 20. So, again, each example I do, I'll try to make similar to a couple problems that you're doing on your assignment so you can always look back at this for extra help if you need it. Okay? Um, so what I'm going to do before we start this problem is I'm going to write our power rule right at the top of our page here. So this means the integral, or the antiderivative, of x to the n with respect to x is equal to x to the n plus 1 over n plus 1 plus some constant at the end. Okay, and this would make sense if we're working backwards from the derivative, because usually when we take derivatives, we subtract 1 from the exponent. So if we're working backwards from the derivative, we want to add 1 to the exponent, right? So that's why this should make sense. Okay, so the first problem says, find the integral of 10x to the fourth minus 6x to the third plus 5 with respect to x. Okay, so what I'm going to do, there's nothing to simplify here. There's no like terms to combine or exponents to get out of the denominator or anything like that. What I'm going to do is just jump right to our formula. So that's going to be equal to, okay, I'm going to keep my constant, and then I'm going to have x to the n plus 1. So that would be x to the 4 plus 1 is 5 over, in the denominator I have n plus 1. Okay, I'm just looking at this first one. 4 plus 1 is 5. Okay, and then minus, keep my constant, 6 x to the n plus 1, so 3 plus 1 is 4. Okay, over n plus 1, so 3 plus 1 is 4. Okay, so one thing I should have mentioned before we start is consider these exponents your n's, right? That represents your n in this formula. Okay, and then plus 5. Now I'm going to have x to the n plus 1. There is no x here, so consider this like x to the 0. But now if I add 1, it would be x to the first. So x to the, I don't have to put 1 right here, but there's a 1, over 0 plus 1 is 1. Okay, and then we always have a constant at the end that we have to add in. Okay, big key with all these problems is to simplify wherever you can simplify. So that means if you can divide fractions, divide them out, get a nice clean number. If you do happen to have negative exponents, you want to move those. You don't want a final answer with negative exponents. So what I'll do is I'll make this 2x to the fifth. I'll make this 3x to the fourth over 2. Okay, and then I'll make this 5x plus a constant. Okay, one thing we always want to do, because it's easy now that we know how to do derivatives, is we always want to check our work. Okay, that's one way that you know if you've done the problem right or if you've done it wrong, is you can work backwards and check your work. So if this is the original function, if we take the derivative of this, shouldn't we end up with this? Okay, so let's check that. If I take the derivative of this, that would be 10x to the fourth. That works out. If I take the derivative of this, that's 12 divided by 2 is 6. X to the 4 minus 1 is 3. 6x to the third, so that gets me back to here. The derivative of 5x gets me back to 5. And there might have been some constant at the end of here that dropped that doesn't show up over here. Okay, so this works. We checked our work. This is our original function. Okay, this was the derivative, this was the original. Okay, so there's example 1. Okay, let's try a couple more examples. This one I want to give us opportunity to work with some radicals. So this one would be similar to number 18 on your homework. Okay, so again, I kind of lost it here, so I'm just going to rewrite this up here. The integral of x to the n is equal to x to the n plus 1 over n plus 1 plus your constant. And again, one thing I forgot to say at the start of all this was n represents your exponent. Okay, so that's where this n comes from. Okay, all right. Before we do this one, whenever you have radicals, just like when we're doing derivatives, it's a lot easier if we convert them to exponents. Okay, so if you remember in the past, we've always taken something like, for example, square root of x, and we would change it to x to the 1/2, right? Those mean the same thing. Okay, so what I'm going to do is rewrite this integral to be x to the 2/5. Okay, so there's my 2, there's my 5, it becomes x to the 2/5. Okay, plus 3 dx. So all I did there, I didn't find anything. I didn't find a solution to the problem. All I need to do at the first step is to rewrite anything that requires rewriting. Okay, so moving forward, let's jump ahead a little bit and let's use our power rule. So I'm going to say x to the, and then 2/5 plus 1 is going to be 7/5 over 2/5 plus 1 in the bottom is 7/5. Okay? Plus, now I have a 3, so there was no x here. But now I'm going to have to add an x. So this is 3x to the 0 plus 1 is just 1. Okay? Over 1. Plus a constant. Okay? Okay, again, I added 1 to here. Got my 7/5, top and bottom. There was no x right here, so consider that x to the 0. But now I'm going to have an x because I have to add 1. 0 plus 1 gives me x to the 1st. Okay? All right. Again, big thing with these problems is you can get, sometimes it's easy to get to the first step, but you always have to make sure you simplify in order to get full credit on a quiz, for example. You want to simplify if you have fractions in the denominator, okay? So if you have a fraction in the denominator, just remember that dividing by a fraction is the same thing as multiplying by the reciprocal, okay? So if I have 7/5 in the denominator, it'd be the same thing as multiplying by 5 over 7. So I could say 5x to the 7/5 over 7, okay? Essentially what I did was I took this and I flipped it, or took the reciprocal, and put it out front, okay? And then plus 3x plus a constant, okay? All right, and that should get us back to our original, okay? So if you were to take 7/5, multiply by 5, 7 times 5 is 35, divided by 5 is 7, but then you subtract 1 from here, that should get you back to 2/5, okay? 7 over 7 would cancel out, and then you have the 2/5. If you take the derivative of 3x, you would end up with 3, and then you've got some constant that you might have lost here that got lost in the shuffle, okay? So you always put your constant at the end. Okay, so there's the answer to number 2. All right, let's try one more, and this one should go a little bit quicker. I just want to give you one where you have an exponent in the denominator here, a variable in the denominator. So x to the n dx is equal to x to the n plus 1 over n plus 1 plus our constant. So let's follow that, okay? All right, similar to the last one, let's rewrite this to, let's get this out of the denominator and make this a power, because just like when we're taking derivatives, when we're taking integrals, it always helps to have powers, so that way you can use your power rule. So I'm going to rewrite this as 4x to the negative 6th dx. Okay, all I did was take this and move it upstairs. Okay, so if I do that, let's take the integral of this. I keep my constant, x to the n plus 1, so negative 6 plus 1 is negative 5, over n plus 1, so negative 6 plus 1 is negative 5. We don't have anything after this, so this would be just plus a constant that we might have dropped. Okay, I would, again, just remind you guys that these need to be simplified. we don't want an answer with a negative exponent. Okay, so let's rewrite this as negative 4 over 5x to the positive 5 plus c. Okay, all I did was pull my negative out front and take my negative exponent downstairs. Okay? All right, guys. Practice problems are listed 11 through 20. Please reach out to me when you have questions. I know this is a new concept here, but hopefully this helped. And again, please reach out if you have questions.